Okay, thanks. I might even need the extra 2 minutes, actually, I don't know. Okay, so this is joint work with Sadegh Dalwandi, who was my postdoc. He's now moved to industry. But we're looking at implementing and verifying release-acquire transactional memory in C11. So thanks to the previous speaker for introducing weak memory. And yeah, we'll be using some aspects of that here. So the classical example that I'd like to start with is this one here, which is called message passing. Now, this is a very well-known litmus test. The idea is that we've got sort of a producer thread here and a consumer thread over here. And what's happening is that we're assuming all shared variables are initialized to 0, by the way. And the producer is sort of writing 1 to X and then setting a flag, which is Y, to 1. And the consumer is kind of waiting for that flag to be set, and it's sort of if that's been set, then it goes ahead and reads the shared memory X. Now, surprisingly, under this RC11 memory model, what can happen is that even though this thread is guaranteed to have executed after this Y has been set, the thing that can happen is that these variables can be relaxed atomics, which means that it's still possible for this read to return the initial value for X. So the postcondition that we can guarantee is that, sorry, this is a little bit annoying, I'll try to use this. So if A is 1, meaning that this thread has seen that right, the value that's returned, it's still possible for B to be 0 or 1. So it's still possible for this thread to read the initial value. The way to fix that, in C11 anyway, is to use these things called release-acquire atomics. And so what happens there is that you introduce an annotation to a write called a releasing annotation, and an annotation to the read called an acquire annotation. And if this read happens to read from this write, what that enforces is the happens before relation between this thread and this thread. And so that enforces a global order between that write and this read here. So essentially, if you insert the release-acquire annotations into this program, you're guaranteed to get that if this thread sees that write, then the value for X that it sees is definitely that write. Okay, so it's not relaxed anymore. So this is the example that everyone kind of knows. One question you might ask yourself is, what happens if you happen to have, say, a CAS that you use for synchronization? Again, we're assuming that all the variables are instantiated to 0. And the way these CASs are written, we're guaranteed that the ordering of the CAS is, this CAS is, if they both succeed, it's this CAS, then this CAS, right? So we're guaranteed that this whole thread has executed before this thread starts writing. And now the question is, what happens, what do we get as a postcondition here? Okay, so it's something you might not know. Well, if you look at the C11, reference manual, you'll see that there are many different types of CASs that they've specified. And in particular, yeah, so there's many different types of CASs, but in particular, the thing that we might be interested in is this one here, which is close to what we want to model. And you'll notice here that there are memory orders that have been specified within the CAS. So there is a memory order that's specified for a successful CAS, and also a memory order that's specified for a failed CAS. Okay, so you can say what release-acquire guarantees do I, or relaxed guarantees do I provide to the client using this CAS. Okay, so we can now come back and solve, or at least answer this question. And the question is, well, the answer is, if you happen to use a relaxed CAS, even if the order of the CASs is that CAS happens before this one, you're not guaranteed any synchronization across the client variable, which is the X. So you could have that this CAS succeeds, and which means that we go ahead and read this X, but this X could still read the old value for return the old value for x, right? This read can still return the old value. So even if A is true, then the value for B could be 0 or 1 as a postcondition. The way to fix that in the C11 memory model is to make sure that this CAS is a releasing CAS and this CAS is an acquiring CAS. And that enforces the happens before relation as before between the successful CAS here and this successful CAS here. And in turn, that guarantees that this client write is propagated properly to the client read over here. Okay, so in this case, if A is equal, if this test succeeds, then the value for B is definitely going to be 1. Okay. So now the question we're asking is whether these sorts of abstractions or these ideas extend to other concurrency abstractions, and what we're looking at are release-acquired transactions. Okay, so it's transactions with annotations that sort of tell you what kinds of guarantees you're providing to the client. Okay, so this is what we had for before, and now we're going to sort of extend this and have, we'll develop a transactional way of synchronizing clients, okay, but also synchronizing the transactions themselves as well. So what we're proposing is that we extend the transactions themselves with some kind of annotation in the same way that the CASs have some kind of annotation. And the idea is that, again, in this example, we're guaranteed that this transaction, this whole thread executes before this thread. If this branch, if this test succeeds. And here, because the annotation is relaxed, the value that you read for x could be 0 or 1, so it could still be relaxed. It could still read the sort of initial write. But over on this side, this transaction, if this test succeeds, has to sort of read from that one. And because we have a releasing annotation there and an acquiring annotation there, what it does is it enforces a happens before relation in the same way that the CAS enforced happens before relation. And here we're guaranteed that the value that you read for x is going to be 1. Okay, so that's the difference. And so this is the new specification that we've come up with. And we're sort of proposing that we sort of use this instead of the standard transactional operations that exist at the moment. Okay, so you might be asking, well, what else can you do? Well, in the transactional world, you can also wrap entire operations around transactions. So here we have this program. This was the message passing that was quite weak. It didn't really do the message passing. But what happens if we wrap the whole thing, the whole left thread in a transaction and the whole right thread in a transaction? Even if these relaxed, even if the transactions themselves are relaxed, we're guaranteed some kind of serialization between this transaction and this transaction. So what we're saying is that in our specification, even though these things are relaxed, we're guaranteed that if this thread reads from that, then we're going to get that this read returns 1. Yeah. And you can also chain together transactions. So this is a release acquire transaction now. And the way this is structured, it's a bit sort of tricky to read because it's concurrency, but the way it's structured is if this test succeeds, then we must have that transaction executed first and that transaction executed second, and that's the third transaction executed. But what we have is this transaction has to have read from that one, and this one has to have read from that one. And this is a releasing transaction, this is a release acquire transaction, and that's an acquiring transaction. So we're going to get sort of this chain of release acquire synchronizations going across. And what that means is this client write over here is propagated over here, and this client write over here is also propagated over here, right? So that's kind of the other part of the specification that we guarantee. Okay, so that's kind of like an overview of the transactional or release acquired transaction specification. So how do we actually provide a semantics for this? So the semantics is based on this thing called a view-based operational semantics for RC11. Now this is different from the axiomatic style that we've seen in the previous talk. And the other part of the specification comes from this existing spec called TMS2, which is an abstract transactional memory specification. So there's these two existing bits of work. One is the RC11 memory model, which is based on views and so forth. Well, that's one way to describe it. And the other part is the specification for transactions themselves, which is defined using TMS2. So essentially what we've done is we've kind of mashed the two things together to obtain a new type of transactional specification, which we call TMS2-RA, and that kind of provides the right thing that we need. Okay, so TMS2 is the specification that sort of defines, well, it guarantees another property called opacity, which I won't really describe in too much detail, but essentially what it guarantees is that all the committed transactions are somehow serialized in some global total order. And then the other thing we need to worry about in transactional memory is what happens to aborted transactions. So here in TMS2, it guarantees that the aborted transactions are somehow consistent with the serialization order of the committed transactions. Okay. And then there's also what happens with transactions that are in flight, so things that are ongoing. These also have to be somehow consistent. Well, they behave as aborted transactions, which means they're consistent with the serialization order. So it's kind of quite a strong guarantee that opacity provides. And TMS2 is somehow a little bit stronger again. And TMS2, sort of the way it's defined is using a sequence of memory snapshots. And whenever you have a committed writing transaction, you append a new memory snapshot onto this M. And read operations can read from a particular memory snapshot. That's the way it works. I'll show you a picture of that in a second. And now TMS2-RA, which is a relaxation, essentially what it does is it sort of tags the memory snapshots as being either releasing or acquiring or release acquiring and so forth. Okay, and depending on who's read from what transaction, you're guaranteed some kind of client-side synchronization. So here's an example of a view-based transactional state. Here we have the memory snapshots, the sequence of memory snapshots, and here we have some client variable. And the way to read that is that time is sort of going down this way, and tau1 and tau2 were sort of two threads, and they have a particular view of the state. And in this particular state, the way it works is that you can read from your view onwards, so your view down kind of thing. So thread tau1, which is here, it can read x is 1, y is 1, and z is 1, okay? Thread tau2, well, for the client variable z, it could read either 0 or 1 because its view is back here. So it could read either that right or that right. And for x, well, for x and y, it could either read this snapshot, which means that it reads both x is 0 and y is 0, or it reads from this snapshot, which means x is 1 and y is 1, okay? So the thing you're not allowed to do is you're not allowed to mix and match at the level of the memory snapshots. So you can't go x is 0 and y is 1 kind of thing. That's not possible. Okay, so that's the basic idea. And so here's what happens as an execution. I'll just show you an example execution in our operational semantics when we execute this program here. And this is a program where we had a relaxed transaction, and we're saying that the relaxed transaction doesn't guarantee any client-side synchronization. Okay, so we've got the client variable over here, and so memory snapshot, it just contains a single location. Okay, and it's a relaxed transaction. That's the initial state. So now let's execute all of the first thread, so thread tau1. So we get a new write for x, which is over here, and we get a new memory snapshot for y, which is over here. And we also have an annotation on the memory snapshot, which says it's relaxed, right? Because that's what the annotation is over here. And the views are also updated correspondingly. Okay, so now let's go ahead and execute the other thread. Well, we're going to execute it in a way where we're forcing the other thread to read from this transaction. But you'll notice that because it's a relaxed transaction, we're not updating this view over here, which is the client-side view, because there's no sort of release acquire synchronization that's induced. Okay, so here the view of thread tau2 of x is unchanged, even though its sort of view for the transaction has progressed. Okay. Let's now sort of change this slightly and put the release acquire transactions in there. So that's the initial state as before. That's the state after executing the first thread. And here we notice that the difference is that this transaction snapshot contains a releasing annotation. Okay, so what happens after I execute this second thread, tau2? Well, because we have an acquiring transaction reading from a releasing transaction, you're guaranteed the view is also updated to whatever the view of this thread is. Okay, so essentially the semantics will guarantee that the view of thread tau2 is also updated to 1, which means that the only thing that you could read when we get down here is 1. Okay, so that's the basic idea. And if we have another example, which is relaxed transactions, well, this is one where you have some initial state, but this time we have 2 elements in our memory snapshot. We're executing all of this again, and we introduce a new memory snapshot. This is a relaxed memory snapshot. And this time, because we're not allowed to mix and match from memory snapshots, even though this is a relaxed transaction, it ends up sort of reading, if it reads 1 for y, it must mean that its view has sort of updated to here, and therefore this read here reads from that x. Yeah, so we don't have to mix and match. That's the idea. And the semantics sort of guarantees all of these sorts of scenarios, plus some other ones that you might want to think about. Okay, so that was the specification. And from that specification, well, you kind of go, well, what's an implementation that guarantees this? Or is there a way to sort of implement this specification? And what we did was we looked at a particular example, a very simple example, because we also wanted to verify this, called the transactional mutex lock. This is an algorithm that's been around for almost 10 years now. And it's sort of based on a library. It's got a sort of begin operation, a write operation, an end operation, and a read operation, and so forth. And I won't go into the details of all of this, but it sort of guarantees the behavior that I showed you before. It guarantees opacity. Well, in fact, it guarantees TMS2, which then guarantees opacity. Okay. Now, what we wanted to do is sort of develop another version of this that would adhere to the more relaxed specification. This time, it's sort of just a modification of the previous algorithm, but we have introduced, we're using sort of relaxed atomics, as well as release require atomics, and the cases have some release require, specific release required annotations and so forth. So it's basically an adaptation of the previous algorithm to fit the sort of release require model. And so given that we have these 2 algorithms now, we can kind of run the 2 together to see sort of what happens. And there's a sort of a famous set of benchmarks called STAMP. And we see that for free, well, most of the time, the SC version and the release require version are kind of are comparable, but in some benchmarks we can see that for free. So here's the blue one is the release require one, and lower is better in this case, and the red one is the SC version. We get sort of improvements for free just because we're using release require. And here's another sort of benchmark where we've got the red one is the SC version, and the blue one is the release require version. And again, we're sort of beating the SC version for free just by changing the atomics that we're using, which is quite nice. Okay, and then there's the sort of proof of correctness, and this is what actually took the longest. So what we mean by correctness in this case is a notion of contextual refinement. Contextual refinement didn't really exist for weak memory until this paper. Well, it did, but not a full version of it anyway. And what we're trying to say is that what we'd like is for some client, when it uses the concrete library, has to be somehow a refinement of the same client using the abstract library. And the concrete library in our case is going to be TML, but the release require version, and the abstract library is going to be TMS2, which is the specification I showed you before, but the release require version again, right? And we want sort of this definition here that when we look at the this program, which is the composition of the client and the library, if you restrict it to just the client variables and remove all the stuttering, then these traces must be a subset of the traces of the other one, which is the abstract version. Okay, that's the sort of standard definition of refinement. The thing is, all of this stuff is now based on the view-based model, which has a lot more information in it. But it's reusing a lot of the frameworks that sort of existed for sequential consistent memory. And so this is a little diagram that sort of depicts kind of what happens. That's what the theorem is. And so we prove this thing using a standard sort of notion, which is forward simulation. But this is sort of, this refinement relation is going to be some kind of view-based refinement relation, which kind of, these states are quite complicated because they're talking about the views of all the threads and so forth. So the refinement relation, ends up being sort of quite complicated as well. But you can play the same game that you would play in sequentially consistent memory. You can sort of set up a refinement relation and then show that there's some kind of forward simulation between the two. And this was the hardest proof by far, which was to show that the TML-ra is indeed there is a forward simulation between the TML-ra and the TMS2-ra. So yeah, so it's all correct. Okay, so one final thing I'll show you is to do with using the specification, because we've kind of got sort of two levels at the moment, and what I've shown you so far has been a relationship between this abstract specification and the concrete implementation. There's another sort of aspect to our work, which is clients that use the transactional memory specification. Can you do something to actually reason about those clients? Okay, and this is what we're calling transactional OOPSLA reasoning, but for these weak memory models. And so the story begins with these logics, OOPSLA logics for several memory models. For instance, this C11 one, but we also have one for persistent memory. And when it turns out that when you have these view-based semantics, you can sort of develop a view-based logic, OOPSLA logic, in a fairly easy way. These are the sorts of things that you can do, just in case you haven't come across this before. You kind of have assertions, these are sort of semantic assertions over atomic statements. So this is a semantic assertion that tells you about this is an assertion that tells you something about the view. I won't go into too much detail, but this tells you something about the view of this thread tau. And supposedly, if it reads X, it's going to guarantee to read get the value V. And if we perform this read, but the same thread performs that read, then as a postcondition, we get that the value of A, which is a register, is this value V that you can see over here. Okay, so but these assertions are assertions over the view state. Okay, so yeah, so what I'm trying to say is when you have these things, you can then define some basic properties about atomic statements. And then from there, you can sort of compose, define sort of the standard Hoare triples for compound statements in the fairly standard way. So for instance, in sequential composition, that's sort of the standard way. It's just that these P's and R's, they range over these complicated view-based memory states. Okay, so that's what's come before. The question was whether this would work also for the transactional memory state we have. And here's an example of the sorts of proofs that we can do in our logic. So this is, okay, I've messed up a few things, but this is one of the, so this is the example where you have a release acquire a synchronization between the two transactions, okay? And here's what the OOPSLA proof looks like. It looks fairly complicated, but it's actually not too bad. The main things that you need to sort of focus on are the annotations in red, but essentially it sort of tracks the views of the different threads, and then it sort of eventually says that, oh yes, the view of this thread has been updated properly so that you get the right, this read ends up sort of reading the right location, or the right value. That's super quick. You can read the paper for more details, but yeah, it's all there. Okay. So that's pretty much all I'd like to say is that, yeah, so what we did in this paper is we developed this notion of release required transactions that work quite nicely, or it play nicely with the existing ways of thinking about our C11 memory model. The correctness is based on existing work. This thing that we defined, this is the specification, TMS-2RA, really is sort of a sort of slight relaxation, but also a proper specification that works for weak memory, and it sort of guarantees opacity, but also it guarantees some, if you have sort of release required transactions, we can support sort of client-side message passing, which TMS2 by itself didn't really specify. And then we've got this implementation, which has been proved correct, and there's a simulation-based proof, and this logic that I showed you at the end super quickly, that's also there as well. So a lot of the work, almost all of the work has been mechanized in Isabelle Hall, and you can see the paper for the artifact. That's it. Thank you.
Okay, very good. Questions, please? Yes, I have a question here.
Okay, yeah. Okay, you might expect my question. I'm wondering, have you thought about axiomatic specification for transactional memory?
We have in previous papers,
Okay.
but not here. So yeah, it would be nice to sort of link it up with an axiomatic specification, a denotational specification.
Okay, yeah.
For sure, yeah. I think the tricky thing is sort of separating out the client and what we mean by the client, what we mean by the transaction. Because the release require, really what it's trying to do is it's trying to tell you something about this client-side synchronization guarantees that you get.
Yeah. I mean, I know that those operational models are quite tricky in like fine-grained. You know, you talk about views and buffers and all this stuff, but they are sort of needed to do proofs, right? People don't really know how to do proofs using like an axiomatic specification, I believe. So, but in some sense, the axiomatic specifications, I believe, are a lot easier, and it would be nice if one could come up with proofs using those instead of the operational model.
And I think if we want to talk to people outside our small circle of verification folks, then I think we need those axiomatic semantics that you speak of. So yeah, definitely we need that, yeah, at some point.
Okay, other questions? I have a question. So it seems like in your semantics, you're preventing the order of instructions inside transactions, is that right?
In my semantics, sorry?
In your semantics, it seems like you're preventing reorderings inside a transaction.
Inside the transaction.
Because in your message passing example, you said if I put both accesses inside a transaction, then the bad execution doesn't happen, right?
Maybe you could sort of point me to a particular slide.
Yeah, if you go back, I thought that's a little bit strong, but I want to hear what you think about it.
So this is, well, by the way, we're using RC11. Sorry, which slide should I stop at?
There was one where you put both axes inside. Is that? I think
yes,
this is the one.
Here.
Yeah, okay. And then you say, well, it's strong enough to say that B is 1, right?
Yes.
But you know, if you have like normal mutual exclusion, like in locks, using locks, reorderings can still happen, right? This seems to be a bit strong.
You mean you could reorder these operations?
The two writes in thread 1, if you reorder them, can you reorder them?
Not in the specification, no.
Yeah.
We're just allowing it in the spec itself. Yeah. One of the reasons is because we're using RC11, and RC11 enforces program order.
Inside the critical sections too?
Well, inside the entire. So the thing is, we're going to be able to implement this specification. I mean, this is a specification, so we can say whatever we want here.
That's right. So I'm saying in the design of the specification, it seems to me that this is a little bit too strong.
It could be, yeah.
Like for example, sequential consistency for race-free programs doesn't need this. You can still reorder inside critical sections, and you still get sequential consistency for race-free programs.
I see what you're saying. Yeah.
You know what I mean? But just some thoughts.
Yeah. That's
maybe it can be relaxed a little bit more.
Potentially, yeah. That would be interesting. Yeah.
Yes.
Yeah, for sure. Yeah.
Okay.
We're trying not to be too radical.
Yeah. So other questions? No, very good. So coffee is waiting for us. Thanks so much, everyone.